Hi, everyone. I'm going to be talking about QSIPrep. QSIPrep, which is some software our group's been working on for a couple of years now. I'm going to start off with some background, which the development began in 2018, back when fMRI prep was starting to be widely adopted among fMRI researchers. And fMRI prep was a pretty noteworthy piece of software because it had some major advantages over other fMRI pre-processing tools. So one of the big things that it did is it used software from many different packages. So included in fMRI prep were AFNI, FSL, ANTS, C3D, and a whole bunch of NILearn. It made sure that the data going between the software packages when you switched from one to the other was correctly handled by the downstream software package. And probably the most amazing thing that fMRI prep did is it would look at the metadata that comes with the data. So as long as the input data was in bits, it would see what sort of images were available, and it would build a pre-processing pipeline for that data that was as good as it could possibly produce. So if it found field maps and the field maps were configured correctly, then it would use those to distortion correct the bold data. If it found a T1, it would register the bold to the T1. If it found a T2, it would make sure that the proper options were enabled when it ran FreeSurfer on the data. And it was just really nice because all you had to do was make sure that your data was correctly in BIDS format and something good would happen to it that was defensible to reviewers and also internally handled consistently. So one of the other major advances that fMRI prep had was it distributed all of these software packages as a Docker image. So it was a very large Docker image that packaged FreeSurfer, FSL, AFNI, C3D, ANTS, all including the Python installation inside of one image that people would download and run either through Docker or Singularity on a cluster. But that solved one of the main problems that these previous pipelines would have, which is that users were relied upon to install many different kinds of software on many different kinds of systems. And this led to a lot of very, very difficult to debug issues. So by including everything in one Docker image, it's good for reproducibility, but it's also very good for ease of use and ease of helping debugging. And then since the fMRI prep was able to adapt to the available input data, it's important that it tells the user what it actually did to their data at the end. So in order to do this, they would produce these very nice looking visual reports where it would show before and after each of the different processing steps was applied. And at the very end, it would write your methods section for you by looking at the graph that it made for the processing steps and then pulling out the citations and the description of what was actually run. So it was very advanced and it became very popular in fMRI. And our group decided that we wanted to do something for diffusion. And diffusion had a somewhat different layout of software at the time. And the software landscape is still a bit like this to this day, where FSL is almost an inescapable reality of pre-processing diffusion data. If you have shelled data and you want to publish it and you don't use FSL, you'll be asked upon review why you didn't use FSL. So we knew we were going to have to include that. Also, the tools in FSL are very good for diffusion, but there are also a lot of other tools out there that do more advanced things than FSL is capable of, but also have smaller user bases and different file formats and different conventions for things like directions. And we wanted to make sure that we could take all of these, use them interchangeably, and make it so that someone who only knows the metadata about the data they collected could read about a method and then find its implementation in QSIPrep and be able to run the workflow without needing to worry about converting directions between software or managing file formats, or skipping one of the steps that's in one of the many tutorials available online on how to do these large convoluted pre-processing pipelines. So one of the other big motivations for us is we wanted to make sure that all sampling schemes are supported. So like we said earlier, the FSL workflows only work for shelled schemes, so either DTI single shell or multi-shell schemes. We wanted to be able to support Cartesian and random sampling schemes as well. So that was something we knew we would need to create a separate workflow that had similar looking outputs to FSLs. And to get the project started, we copied the entire source tree of fMRI prep version 1.2.6, or sorry, 1.26. And we did a find and replace and replaced fMRI-Prep with QSIPrep. And it turned out that just the way that diffusion data is collected and the steps that have to happen to it, it's sort of fundamentally different from how bold data is handled. So we ended up rewriting almost everything except for the anatomical and the distortion correction workflows. But because we did this initial find and replace, we kept the really nice parts of fMRI-Prep, which is that it was beautifully coded. So the design of the software itself, including its CI/CD setup and the way that it creates NIPIPE workflows based on the input data, all of that is still there. So if you know how to work on fMRI-Prep, it will be very easy to go into the QSIPrep source code and change things there. And so it superficially looks similar to fMRI-Prep, but has a lot of differences in it. And in fairness, we also are missing some of the updates that have happened to fMRI-Prep's anatomical workflows since 1.26. But in addition to that, we also added a new motion correction algorithm that works on any non-single shell scheme that we call SHORELine. So it works for multi-shell data or Cartesian and random sampling schemes. And we added what we're calling curated reconstruction workflows. So reconstruction workflows where we go across these different software packages such as Dipy, DSI Studio, MRTrix, Amico, and you can put them together in a config file and mix and match them. So you can do reconstruction in Dipy and then tractography in DSI Studio, or reconstruction in MRTrix and do tractography in DSI Studio, and mix and match. It's one of the more fun things to do, and there will be some examples of that at the end of it. But the reconstruction workflows, in addition to being able to do custom things, also have the most vanilla, not incorrect versions of published pipelines, so that if you read a paper and say, I want to reproduce this reconstruction workflow, we have a list of them that are supported, that we've consulted with the developers of the original pipelines, and we know that the necessary steps are in there. So we borrowed some philosophy ideas from fMRI-Prep. We try to use the best tool from each software package. Luckily, in the diffusion world, there aren't too many overlaps in functionality. So we went to great pains to make sure that data is transferred correctly between software. And we also made sure that each of the steps that happens to the data is accompanied by a report, along with information about the software that was used and the parameters used in it. We handle field maps, which is one of the things that separates diffusion from fMRI. There are very weird things that diffusion acquisitions tend to do in order to get distortion correction, things that are a bit more creative than how bold acquisitions typically handle it. So we made sure that we handled all of those, which turned out to be one of the more difficult parts of developing this, because the bid specification isn't great for diffusion images yet. It's one of the things that they're currently working on. So we had to add some extra workarounds to handle the lack of specificity in the bids for diffusion. And then one of the other things that we do is each of these softwares computes structural connectomes and then stores them in many different file formats. We make sure that at the very end of the pipeline, all of the connectomes that are made are stored in the same format in the same file. And we basically, every way that you can compute a structural connectome from each software package is included in the output. And lastly, what we borrowed from fMRI-Prep as well is we continuous integration test each of these workflows. So every time before we make a release, we make sure that at least basic functionality hasn't broken. So the secret to making QSIPrep and the other preps work is that the data has to be acquired and converted into bids format. So one of the big issues with diffusion data is a lot of times groups won't have someone who specializes in it. And so the data will be collected and it's handed off to a student who doesn't really know how the data was acquired or the details of it or why it was acquired that way. And they want to pre-process the data, but they don't really know how they want to, or whether the data they've collected is actually compatible with the method that they're proposing to pre-process it. So to get around all of these problems, you can just make sure that the data is converted into bids format, which is mostly completely supported by all scanner vendors. The DCM to NIIX software does a really good job of pulling out metadata and making sure that the metadata is Following the BID standard, with a few file renamings, you can usually get your entire data set into valid bids. And once it's in valid bids, then you can also, if you have more than a few files you need to rename, there's software called QBids that can help with that as well. And as long as it's valid bids data, then the pipeline will be run correctly. So what does that mean in practice? It means that as a student, you would install Docker or Singularity on your cluster. You would ensure that your data is bids valid, and then you run a QSIPrep command and wait for the results to come out. So what exactly is a QSIPrep workflow? This is the overview of all of the things that can happen to it. This was included in the paper and is already a little bit outdated, but we'll go through each of these steps in turn. So the first part is coordinate systems are a huge problem. So even in the BIDS specification, they technically say that your BVALs and BVECs should be in the FSL format. Well, the FSL format is not simple because it actually assumes that your voxels are in a specific orientation. So there are two different ways that people use BVECs, and this has hurt a number of software packages, but it can be unclear which direction the BVECs should even be pointed in. So the first thing that QSIPrep does is it checks the orientation of the images themselves to determine whether the BVECs are likely correctly oriented or not, and it forces everything into the exact same voxel and BVEC orientation. So there's an initial conversion of those images and the corresponding gradients. Once this has been done, then we move on to the part where we're going to figure out which images look similar to one another based on their EPI distortion. So on the bottom right over here, we can see a couple of images that have LR and RL phase encoding directions, and there's just massive geometric distortion in the image itself. And so certain pre-processing steps you don't want to perform on just concatenated versions of these images because it's physically different tissue that'll be inside of those voxels. So QSIPrep goes through and it tries to find warped groups, and these warped groups are, I guess that's the next slide here. They're images that all have the same phase encoding direction and total readout time. And by default, the warped groups undergo the initial denoising steps, which are the next couple of slides, together before they're concatenated, and they're concatenated before they go into top-up and eddy. But you can also combine those images before you do denoising if you'd like. It's an option for users. But these warped groups are detected, and they have to be detected automatically because the BID specification, at least BIDS 1.0, didn't have an option to use a DWI image to distortion correct another DWI image. So oftentimes acquisitions would have one set of AP phase encoding directions followed by another set of scans with PA phase encoding directions, and you would extract B = 0 images from each of those, use those in top up, and that would be your distortion correction. So the original BIDS assumed that there would be something in your field maps directory that would be used to correct your diffusion scans, and that's not always the case. So by directly grouping scans into warped groups, we get around that issue with BIDS, and it puts us in a good position to figure out what sort of distortions are available in order for us to estimate the EPI distortions, which happens later on. So grouping by distortion and doing the susceptibility distortion correction, one of the other issues with it that we solved, or that we copied a technique from the developing human connectome project, was that we use this best B = 0 image method. So one of the things that is very common in scans in both the DWI directory and in the field map directory is that you'll get multiple B = 0 images per scan. And top-up is only expecting a few example B = 0 images from each warped group. So we take all of those B = 0 images and calculate pairwise image correlation between them and find the image that on average correlates with all of the other images the highest. And you can rank those and pick the top N of those to go into top-up as your representative scans for doing distortion correction. This ended up being really important for child and infant data, where oftentimes the person in the scanner will be moving their head a lot. And if you just take the first B equals 0 or a random B equals 0, you'll find one that either has huge motion artifact or a lot of striping, and that ends up making top-up perform relatively poorly compared to the performance you would get with nice clean images from each distortion group. So it'll take out B equals 0 images from both the FMAP and the DWI directories in order to perform distortion correction. After that's done, top-up and eddy are both configured using the BIDS data that was your input. So one of the other main obstacles for running top-up and eddy is that they both have configuration files that are kind of strangely configured and not very intuitive. So as long as we have valid BIDS data, there's enough information in the BIDS data for us to automatically configure the input files for your top-up run and your eddy run, and those are added in as well. Since eddy has so many arguments, we set a bunch of defaults, but if you're an eddy expert, you can supply your own set of eddy arguments and give those to QSIPrep when you run it, and it'll send all of those into eddy when eddy ultimately ends up being run. So the next step that happens after these images are grouped together is we do denoising, and there are 4 steps that can happen. Gibbs unringing is the first one, which is done in MRTrix. And that one isn't turned on by default because there's an assumption with the MRTrix Gibbs unringing that your images have full Fourier acquisition, which is not always true. If you know it is, or if you're willing to use the method despite not having the full acquisition, then you can enable Gibbs unringing with a flag on the command line. The next part that happens is image denoising. By default, it uses MPPCA from MRTrix, but we also have patch to self enabled. Once denoising is done, then you move on to bias field correction, which is done using N4 bias field correction from ANTS. And then the last step is a B equals 0 intensity harmonization, which is where the B equals 0 images, their average intensities are calculated, and the corresponding, or the nearest images to them have their intensities matched to it. So if there's signal drift throughout the entire scan, as detected by looking at the B equals 0 images, then it can go in and adjust them. Also, if there's just a large scale signal difference between individual acquisitions, so say your sampling scheme was split up into more than one run, you can intensity harmonize the B equals 0 images across those different acquisitions. These are all also available to be turned off. So this is one of the examples of what the visual report looks like for the Gibbs unringing step. It shows a low B value image, and then it shows the detected ringing that it's subtracted. And it looks pretty good here. The next image that I'm going to show is the visual report from MPPCA. So one of the things that's plotted here is a contour map of the noise image that's calculated by MPPCA. Patch to self also collects one of these, and it shows the average magnitude of the noise that it's subtracting. And one of the things that the MRTrix folks recommend is that if you're looking at the noise image, it shouldn't have anatomical features in it. It means that you may be overfitting in your denoising. So you would want to change the radius that you're using. This next one is a MPPCA where we don't see those in the image, and I mean, besides eyeballs, but that's okay. You don't see individual ventricles or anything like that in this version of it. If the slides were a bit higher resolution, you may also see the images, both in the previous one and in this one, go from having some fairly clear noise in them to looking much better. The next denoising report that we see is the bias field correction. And so the raw image is displayed, and then after it's had its intensity normalized, you see what that version of it looks like. And the actual bias field itself is plotted as a contour map. And this one looks like it had higher intensity near the coil, for example, and lower intensity in the middle. And after bias field corrections applied, it looks much more uniform across the slice. Next up is my favorite. This is susceptibility distortion correction. If you can see it on your screens, there are little blue contour lines that show the gray matter, white matter interface from the tissue segmentation that happens based on the T1 weighted image. and it shows you the before image where there's clearly distortion, and this is an APPA scan, and the after image after the correction's been applied, and everything just happily goes where it's supposed to go. So these are all inside an HTML report that you scroll at the very end to make sure that nothing crazy's happened. The next portion of the pipeline is head motion correction, and additionally eddy current correction, depending on which version of the pipeline you use. And which version of the pipeline you use depends on which sampling scheme that you have. So if you have a single shell DTI style scan, or if you have a multi-shell scan, then you can use FSL's eddy, which will do head motion correction and eddy current correction. If you have multi-shell Cartesian grid diffusion spectrum imaging style acquisition, or a compressed sensing DSI with a random acquisition, then you can use our SHORELine method for motion correcting these. So eddy does a lot of things. Among them, for motion correcting the data, it estimates a Gaussian process model per shell, and then uses that to try to estimate predicted images that it registers the actual observed images to. It'll also fill in slices that it thinks have dropped out, and it will try to apply some nonlinear correction to the image to account for eddy current distortion. What SHORELine does is it's a leave one out iterative algorithm where it goes through and it will remove one image, fit 3D Shore to all of the other images, and then it will predict the left out image, and then it uses ants to register the left out image to its predicted image from the 3D Shore model. And it does this for every single image, and then applies those corrections, estimates a new model, and does this until the motion estimates converge. And because ANTS does not currently have a quadratic deformation model like eddy uses, we don't do eddy current correction in SHORELine, but we did test that it actually works with some benchmarking. So our benchmarking test for the SHORELine head motion estimation was we took the FiberFox software, which starts off with a set of streamlines, and we took known translations and rotations and applied them to those streamlines. Then FiberFox took each of the transformed or untransformed streamlines, simulated a case-based signal acquisition based on a cell compartment model and the response to it, and gives us an entire sampling scheme. And we tested the ABCD sequence, the HCP sequence, a 257 direction DSI, and then a 55 direction compressed sensing DSI. And since we manually moved the streamlines before we simulated the scan, we know exactly what the ground truth motion was, and we can detect, or we can compare the estimated motion from the motion correction algorithm to the motion that we know was there, the ground truth motion, and get an idea of what the mean error is. So you can calculate an RMSE between the real motion and the estimated motion. And the good news is both methods work shockingly well. So in ABCD and HCP, the voxel size that we simulated was 2 millimeters, and the errors are almost all less than half of that. Rotation depends on a lot of things, like whether you denoise it or how many volumes were moved during the actual simulation. So this is kind of a dense plot. In this first cell here, the 15, 30, and 50 corresponds to what percentage of the volumes in the scan were actually moved before the signal was simulated. So very low motion, everything does wonderfully. 30% motion, performance goes down a bit. And then 50% motion, the trend continues. But either way, all of this is still very good news. SHORELine works well, works comparably to eddy, and it generalizes all the way to Cartesian and random sampling schemes. So we've got head motion covered, eddy current correction, maybe someday. And in addition to the diffusion processing, there are a few multimodal things that'll happen. So this is the T1 weighted image to the diffusion reference. And this also is done using ants, and it shows you the before and after animation here. And lastly, it'll also use ants to do, this is the T1 to the T1 template using ants as well. So it shows you, this is the template, the one that looks cartoonish, and then the actual image warped to the template is the one that says moving. So this registration is only used to bring atlases from the template space into the subject's native space. And at the end of the day, all of the images that come out of QSIPrep are not technically in the subject's native space, but they're in ACPC aligned orientation, aligned in world coordinates to that person's T1 weighted image if that image is present. So one of the really important things about the QSIPrep pipeline, which is something that's shared with the fMRI prep pipeline, is that each of these steps, whenever there's a spatial transformation that's involved, so things like distortion correction, motion correction, we don't want to keep on applying those transforms and then continuing to process, because each transform involves interpolation, which adds additional smoothness to the images. So instead, what we do is we combine all of the transforms and then do a single shot interpolation at the very end. This ends up giving us much crisper results. And that's one of the things that we quantify in our comparison to other pipelines, where you'll have anywhere from 3 to 7 interpolations that happen from the beginning to the end of pre-processing. So the output of QSIPrep is some parts similar to fMRI prep. We have a confounds TSV, which gives you the head motion, but it also includes the B-val, B-vec that correspond to that image. And then each step that occurs, so the bias correction, the denoising, the unringing, the change in average signal intensity for that image is included in the column as well. So you can see which steps in the processing pipeline are having large effects on the actual signal in each image. We have a DWI reference image, which is a sharpened version of the B=0 average from that scan. The B-val, B-vec, and nifty, those can go directly into Dipy. And the .b is for MR tricks. So one of the issues is that the orientations that are used internally inside of QSIPrep is LPS+, which is the same as the internal coordinate system of ANTS. And that makes the rotation of gradients and the transforms of images really easy to keep track of. The B-val and B-vec format only works if the images and the B-vecs are in the same orientation. And since FSL is expecting a different orientation, it doesn't work. So MRTricks interprets these incorrectly. If you use the .b file, it will work perfectly with MRTricks. We get a brain mask. We get information about the optimization for the head motion correction. And in the anatomical directory, you'll have the T1 weighted image after it's been processed, skull stripped, and segmented. And there's a little HTML file that comes out at the very end that shows what happened during your processing. So these are some of the other components. I showed you the before and after images that are presented during the HTML file. This also shows, for example, here's one of those Cartesian grid schemes, and it rotates around in a little GIF, and it shows you what that scheme looks like after you've done your pre-processing. So here, this image got rotated when it was aligned to the T1 image and then aligned to ACPC space. So those BVECs also have been transformed, and it's just a sanity check that that's happened. And since we used SHORELine for this, because we can't use eddy on these grid schemes, it shows you slice by volume what that slice's cross correlation was with the predicted image that came out of SHORELine. eddy shows something similar. So here we have a multi-shell scheme. Here's the lower shell, here's the higher shell. You get frame-wise displacement plotted, and eddy shows you the opposite in its carpet plot, which is what is the standard deviation of this slice at this image number. So little bright speckles here means that there was likely a slice dropout, and then areas where it's kind of patchy is probably part of where the brain isn't very present. So the last part of these carpet plots over here, instead of segmenting tissue, because fMRI carpet plots, you have all of the voxels as the rows in this matrix, and then the columns are the time points. We're doing slice by time point. And so this little bar over here shows you it's color coded by the number of in-brain mask voxels you get in that slice. So you really just want to pay attention to where we have a whole lot of brain, how big are the number of standard deviations from the expected image. And then the last part of the HTML report is this methods boilerplate. And so as QSIPrep goes through, it uses NiPipe. As it goes through and it builds the workflow based on what it sees inside of your data, it grabs the boilerplate text that goes with those nodes, and it does a breadth first search for through your processing graph and pulls out this text. So it grabs in order the steps that were actually applied, and then it also fills in the references to them. So this is probably too small to see, but there are some examples in the paper and then also in our CI testing that you can look at. And it tells you exactly how eddy was set up, how top-up was used, where the images came from. Internally, we use Dipy a lot, so that's a citation that just gets in there by default. But you can copy and paste this into your paper, and it will accurately reflect what actually happened to your images during pre-processing. One of the other things that comes out is a JSON file that's used in the dipymri prep viewer. And that's a separate piece of software, but it's used for doing group level quality control on your scans. So this is a static screenshot of it. And if there's some time at the end, I'll show what these look like when they are actually used interactively. But you can click on a subject, and then here you can scroll through, like there's a little slider widget that you can use, and it shows what the actual images look like as you move through this person's scan, and the images change up here. There's also a color FA and a brain mask image below that. So it's a pretty useful thing for rapidly QCing a whole bunch of scans, and it lets you give the series a definitely not usable, uncertain, definitely usable, and then there's some probably usable or probably unusables you can check as well. You do this on enough of them, and you can get an idea of what some of the automated QC scores mean in terms of this particular data that you've collected. So we set up this whole thing, and how did we test that it actually works compared to the many other diffusion processing pipelines that are out there? So us and a large group of co-authors did this project, and we grabbed a whole bunch of different kinds of sampling schemes where there was an accompanying pre-processing pipeline where we could get both the raw data and the pre-processed data, and run the raw data through QSIPrep and compare some QC metrics to the data that came out of the other pipeline. So some of these other ones, for example, the compressed sensing and the Cartesian ones, there isn't really a pre-processing pipeline that went with them, but we have HBN is a very popular publicly available data resource. We took one of the HCP lifespan sequences, the 103 direction ABCD sequence. The multi-shell 113 was a NODI optimized scheme that had a whole bunch of shells and a few that had only like 5 directions in them. And then we had a classic 64 direction DTI scan, which was what was used in the Philadelphia neurodevelopmental cohort. So we looked at 2 different metrics for each of these schemes. We looked at the full width at half maximum, which is a measurement of how smooth the image is. And in the previous pipelines, we typically saw that the full width at half max was much larger than what QSIPrep produced, mostly because they would have repeated interpolations inside of them. So before more recent versions of top-up, for example, eddy, you had to use applied top-up afterwards. So you would have the interpolation that happens with eddy, followed by the interpolation that happens with applied top-up, followed by the interpolation into ACPC space. And so there were a lot of interpolations involved, and you would end up getting very smooth images. So we show that QSIPrep is generally a little bit sharper voxel-wise. The next metric that we used comes from DSI Studio, and it's called the neighboring DWI correlation. And it's a metric between 0 and 1. That's a weighted correlation coefficient image-wise between your B greater than 0 images. So if you look at an image coordinate in Q space, you can tell the distance between that image and another image. And if you invert that and do a weighted average of their image-wise correlation coefficients, it gives you an idea of how consistent those images are based on how close they are in Q space. So you can calculate that for any sampling scheme, and we did just as well or slightly better than the other pre-processing schemes. And for the non-shelled schemes, the random and the Cartesian, we did better than nothing. So that was also a great accomplishment. So the summary for the pre-processing portion of QSIPrep is that at the end of the day, as long as you get your data into bids, you can run QSIPrep and get out some nicely processed data along with part of your paper. And if you take any of the Dipy example code that's been used throughout this conference, you'd be able to run it directly on the nifty BVal and BVec that come out of QSIPrep. And it's undergoing continuous development. So we recently added options for processing infant brains and macaque brains. And we're in the process of running some large publicly available data. So ABCD and then HBN and NKI all will have QSIPrep pre-processed outputs available to download either from Indy or from the NDA. So that's the pre-processing portion of QSIPrep. Next up, we have Reconstruction. So pre-processing is somewhat boring. Reconstruction is where there's really interesting stuff you can start doing with your data once some of the artifacts have been removed from it. And there are a lot of software packages that implement many cool things you can do with it. And our goal was to combine them in reasonable and accurate ways so that it's easy to apply them to the data that comes out of QSIPrep. So the way that we actually designed this was that any of the reconstructions that you do, so if you use MRTrix, if you have single shell data and you want to use a multi-shell, or sorry, a multi-tissue single shell CSD, there's a fork of MRTrix called MRTrix 3 tissue that works shockingly well, even on clinical quality DTI data. If you have basically any sampling scheme except for random, DSI Studio will correct it. And then under the hood, QSIPrep can take any of the reconstructions from these software and convert it into Dipy. So it'll have the peaks format that Dipy uses, and it'll have the ODF format from Dipy, and then it can go from Dipy to any of these. So that means that we can do something cool like reconstruct CSD multi-shell multi-tissue from MRTrix, and then get it in DSI Studio format. Under the hood, what we do is it goes through Dipy, and then out comes your fib file so that you can look at it in DSI Studio's viewer. And then DMRI Amico doesn't produce ODFs, so I guess we do actually convert it to Dipy first for the peaks, and then send that to DSI Studio, but you can't go to these other ones from it. So this one was also from the paper. We have a couple of interesting areas to look at. We wanted to see how reconstructions do in some interesting areas. So we have single fiber going through corpus callosum, single fiber voxels going through corpus callosum. And then we have a couple of crossing fibers that happen over here in the Centrum Semia Valley. And then here we have 3 different reconstruction methods. So we have GQI from DSI Studio. We have multi-tissue CSD, which comes from either MRTrix or MRTrix 3 tissue. And we have Laplacian regularized map MRI, which comes from Dipy. And so we show the ODFs that come out of these. So for DTI, this was that single shell scheme. So for multi-tissue CSD, that's done with 3 tissue. The rest of the multi-tissue CSDs are done with standard MRTrix 3. And I don't have any statistics on this image, but I think it's nice to see how similar all of these results actually are. And I think the ability to go between the different reconstruction methods and have everything come out in a directly comparable file format is going to make it much easier to determine how similar these methods are to each other, and perhaps benchmark a little bit when one is more appropriate than the other. We haven't done this yet. So this shows that you can take almost anything and reconstruct it using almost anything. And hopefully this will be used in the future by someone. This is another example of crossing across software packages. So the peak directions here came from Amico, and the fiber tracking is being done in DSI Studio. This is a list, and it's available on our documentation of all of the different reconstruction workflows that we offer. So these are ones that we've checked and that we regularly CI test to make sure that they're doing at least what we expect. Many of these are just variations on how the tractography is done. So for example, you'll see MRTrix has 6 different versions. One of them uses no anatomically constrained tractography. This one was recently added. It uses FreeSurfer data and does a hybrid surface volume segmentation using the FreeSurfer surfaces and a couple of other tools from FSL and some tools from ART, which is interesting. And it's very, very good. We added this because we found that the fast version of ACT was not very good and would end up cutting off a lot of connections. So whether you have multi-shell data, which will use regular MRTrix 3, or if you have single shell data where it will use Mr. Trix 3 tissue, both of those will work. And the outputs will look identical. You won't know just looking from the output images whether it was 3 tissue or regular, but you will know from the methods boilerplate that comes out. We also have Amico, which does a really nice implementation of node fitting, and you can view those results in DSI Studio, as well as getting all of the ICVF and ISOVF out of it. We have a couple of different Dipy reconstructions. This, oh wow, this is already out of date. We have Dipy DKI as well. And we also have CS-DSI 3D Shore, which if you have one of those compressed sensing DSI schemes, it'll fit 3D Shore to it, and then it'll extrapolate a HCP or ABCD sequence and run one of those MRTrix MRTrix reconstruction workflows on it, and it does a pretty good job of extrapolating. So just like the pre-processing, we produce HTML reports. So we have ODFs that come from those same 3 regions that we had in the earlier slide. These are all generated using Fury, and they have the methods boilerplate with them as well. It's not included in these slides. And then we also have the peak directions, which is a great way to check quickly that your ODF peaks are actually pointing in the right direction. If your data came from QSIPrep, it should be in the correct direction, but this will alert you quickly if something has gone wrong. And as I said before, also the connectivity matrices, it takes all of the atlases that the user requests, which is every atlas that someone has asked for on a GitHub issue, and then it calculates the connectivity between those pairs of regions using all of the available weightings from that software package. So DSI Studio has quite a few MRTrix. We calculate the SIFT weights or the regular streamline count, and then things like the average streamline length. Those all go in there as well. Speaking of SIFT, if you aren't using it, it's a really good idea for getting around the problem of streamline count being kind of an uninterpretable metric of connectivity. It forces your streamline counts to reflect the actual FOD peak magnitudes that exist in your data, so you don't end up overcounting corpus callosum. We use the SIFT2 weighting extensively in our group. And then here's an example of a scheme extrapolation. So we collected a compressed sensing DSI. We used it to extrapolate a HCP scan, and then we used the MRTrix reconstruction method on it, and it looks just like a normal HCP scan, except that we only acquired 55 images.